Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my pleasure today to introduce Hannah Pasula. It's a special pleasure because I've known Hannah since she was an undergraduate, when I was a grad student back at Harvard. And even back then, she was doing pretty extraordinary things. So it's very unusual for undergraduates to work really closely with professors at Harvard and do actual research. But I got to know her because because she was one of the very few graduate students one of the very few undergraduates who was doing that. So she went on from Harvard to better places. She went to Berkeley, where she got her PhD, and then did a postdoc at MIT, where she worked on introducing probabilistic methods to planning, in particular learning the planning rules probabilistically. And now she's across a very big lake at the University of Washington. And then today she'll be talking about this is the work from your postdoc at Berkeley.
No, this is my thesis work and also current work.
Oh, thesis and current work. Okay. Anyway, so it is a pleasure to have Hannah come talk to us.
Should I start?
Yes.
Yes. All right. Well, I'm Hannah Pasula, and I'll be talking about this problem called identity uncertainty that I will explain in more detail, and about approximate inference techniques for it. And parts of this are joint work of any number of people that you can read about here. All right. So what's this problem? The sort of general problem scenario is that we're in some domain where there's uncertainty in some form, and we want to reason about the objects in that domain, about their properties, or about whether they even exist, about how many of them there are, things like that. And the problem that we have is that the observations we're getting from the domain do not actually explicitly identify the objects, it's not just that they give us noisy observations of their properties. We're not actually sure how they relate to the actual objects. So I'll give some examples now. And the first example is citation matching, and I picked this very special example of it. I'm sure everybody knows CiteSeer, right? And if you try to find a paper by Goodman and Chen on CiteSeer, you will find okay, so the general problem handled by CiteSeer is to take a bunch of citations and to try to sort of cluster them together into citations that correspond to the same paper. So that, and you can see that it doesn't actually do a perfect job because this is a difficult problem. For example, it thinks that this paper exists twice for some reason. And there's a lot of sort of noise here and uncertain, names can appear in various forms. There's not only uncertainty over what papers there are, but there's also uncertainty over who the authors are, and thinking about the authors can help us think about the papers. For example, is this Goodman, who also publishes with a Chen, the same as this Goodman? These are the sort of problems that we might want to think about. And my second example today is kind of different, but it's actually in a sense a very similar problem. It's taking laser rangefinder observations that a robot finds as it walks around a computer science building, and these observations are transformed into a Voronoi graph that fills this space. Basically, you get like sets of observations corresponding to various points in this space, and then you want to try to figure out what kind of location, what kind of place each of these points corresponds to, and sort of cluster them together into specific places like rooms and corridors and doorways and junctions of corridors. And the reason why you might want to do this is so then you can tell the robot, leave this room and go down the hallway, take the second door on your left. things like that. And actually, it might seem like you can extract these places fairly easily just by sort of locally deciding which point is deciding on the type of each point. But it should be sort of clear that by reasoning about the clusters of points, about the whole spaces and their properties, you should be able to improve on those results. All right, and the whole general problem of identity uncertainty, of thinking about these objects that are behind a set of observations, just occurs everywhere. For example, there's the problem of data association, where you're tracking multiple targets. I've worked on tracking vehicles down a freeway. Where you try to figure out which observations of vehicles form different tracks. There's a very big problem of database merging, where you have databases where some of the records co-refer, but you're not exactly sure, and you want to combine them together. There's other planning problems, like re-recognizing landmarks when you see them again, and named entity extraction, all sorts of exciting things. And the general setup is, the sort of general situation that all these problems have in common, is that we may need to think about uncertainty. Since we're thinking about different objects that we have seen or inferred, we'll definitely want to think about inter-object relationships. And also, the specific thing that we'll be doing here is thinking about the identities of objects. So these first two things, uncertainty and the relationships between objects, are handled by a large number, a whole alphabet soup of different representations that combine probability with logic or with other types of relational little additions in different ways. So we'll just pick whichever one suits us. And then we want to extend these representations to handle this new idea of identity uncertainty and to do inference and learning. All right. So I'm going to be talking about the two domains that I mentioned as my example domains before, citation matching and the topological mapping domain. And they're going to be sort of different. This is my thesis work, where we used a directed graphical model and sort of solved the whole problem with it. And recently I've been working on a very similar problem using a discriminative graphical model. And there's some slight differences, but it's basically the same idea. And that's sort of the interesting thing about this, is that it's a problem that occurs everywhere. And the sort of general framework can be used with different kinds of problems. And similar sorts of algorithms will apply. All right, the citation matching domain. Yes, OK, so I'm sure everybody here knows about Bayesian networks, right? But just in case people don't, you have a joint distribution, you factor it taking advantage of independence, of different independencies. You have a graph of nodes and edges. Each node has a distribution that's conditional. That's conditioned on that node's parents, because it's a directed graph. And then the whole joint is just the sum of these conditional distributions of all the nodes, right? The sum, the product. Yes, the sum if you're doing logs. And the one point that I wanted to make here is that this is usually used as a generative model. So if you want to figure out, so these are observed and hidden things, right? So if you want to figure out hidden things, so basically it's often written in the form where you're sort of generating the observations from the hidden things. And if you want to figure out the hidden variable, the values of the hidden variables, you'll have to reverse this thing. Anyway, it's a Bayesnet. All right, more interesting stuff. Relational probabilistic models. So these are going to be sort of an extension of Bayesnets in a way. And the reason why we add this relational stuff to Bayesnets is that it's a lesson we sort of learn with logic, is that in logic, when you have you're going to have propositional representations that sort of give each variable a specific, basically define a specific variable for each sort of specific thing. So for example, if you're making up rules on a chessboard, you'd have a variable representing every single position of every single piece of the chessboard. And then when you're writing down the rules, you'll have to write down rules, like if the pawn is in like 1-1, moves to 1-2, then it will, if it moves across, it'll be in 1-2, things like that. And you can, if you use first order rule representation, you can just write down general rules, so it's much more compact, which of course makes it easier to learn because you need less data. And also, if you're abstracting over objects, you can find that the rules you wrote down are applicable in situations other than the ones where you learned them. And a lot of people are doing research on this right now, as I'm sure some of people know. So the idea is to do the same, to augment probabilistic representations in the same way. And the general approach that I'm going to be talking about here is to sort of define little network fragments that are abstracted over objects, and then you put them together once you know a set of objects into a Bayes net. Is the speed of the talk about right for people? Questions? Too slow? Too fast? All right. So this is a relational probabilistic model. It's best to explain these things using an example. So I'm going to use an example. It's all very object-oriented. You have different classes. This is a citation domain, so our classes are citations, papers, and authors. And classes can have attributes. And there are two different kinds of attributes. There's basic attributes, which take on discrete values. For example, a paper's title can be one of, is a string of characters. Ranges over strings of characters. And then there's complex attributes, which will map to objects, from objects to other objects. And all of these, the values of these attributes, once we build up our model, are going to be probabilistic variables, and they're going to be governed by like probability models of which we annotate this RPM. So the blue arrows here represent sort of the structure of the relations between the objects, and the red arrows are showing probabilistic dependencies. So for example, the title of a citation is dependent on the title of the paper the citation refers to. So it's all pretty clear, right? And okay, so these are classes. We instantiate different objects for them. And the attributes, like I said, become Bayes net nodes. And the dependencies become edges. And then, of course, we need to define all these probability distributions. So here we need a bunch of different priors and some conditional distributions for how things are misspelled and so on. And the only observed thing is the text of the citation. So everything else will be derived from the text in some way. And yes, any questions about this?
So what's the relationship between RPM and graphical model? Or are they fixed?
This is an RPM is like a way of defining a graphical model. So it's defining a set of graphical models, and then once you have a set of these instances, and if you have a set of instances and you know the relationships between them, then you basically have a Bayes net.
No, in Bayes net, each node is a random variable.
Yes.
Now, in this case,
each attribute will be a node and will be a random variable.
But it looks like there's a hierarchy there. You have citation, and then under citation you have a whole bunch of attributes. How is that structure represented in the regular graphical model?
Well, it's not. Once you make the model, it all becomes like a flat normal model. You just take your this. So this is an example for a very simple situation where you have one citation, one paper, and one author. You just follow these red links that I showed here to figure out what is. You basically you just make a little node for each attribute of each instance, and then you follow these red links to figure out where the probabilistic dependencies go. So you see, like I mean, it's all pretty obvious, right? The text of the citation is dependent, sort of made out of modulo some mix-ups. At the citation title, the first names and surnames of the author. In these examples, I'm assuming that each citation just has one author, just for simplicity. And then the citation title is dependent on the title of the paper responsible for it. And here we have this sort of special node. This is a node, a base node that corresponds to one of these complex attributes that map to objects. So this is a node that is going to say which particular paper this citation refers to.
So far you've only shown one-to-one relationships.
Yes.
Or are you double counting with many to one?
Well, yes, I'm going towards that slowly. All right. Oh, actually, I wanted to say just one more thing. How these things are constructed, like in practice. Well, so we're only given the citations. And then for the citations, we create papers and authors as needed to fill the slots of those citations. But of course, it's not that simple. All right, so then we have many citations. So for each citation, we create all these necessary things, right? And then, of course, we want to be thinking about which citations correspond to each paper. So it's not just that each citation has its own special paper. We want to think about whether these two citations might co-refer or something. But this is still not quite right. And the reason it's not quite right is because these representations are sort of constructed on this logical idea of possible worlds. And in general, they make this unique names assumption, which means that each instance that you introduce corresponds to one object in the world. So basically, if you build up these base nets, you end up with all these separate authors that you're thinking about. And in order to have these one-to-many relationships and so on, we're going to have to change that. And we remove this unique names assumption. So now instead of having each paper just map to its one object, the papers could map to the instances could map to objects in any of these many ways, and they could even be an infinite number of objects. Is that making sense? Questions? And so we're going to represent this mapping over here by this thing we call the identity mapping iota. And if you think about it, iota can be represented as an equivalence relation because it basically sort of clusters these things together, right? So if P1 maps to this and P2 maps to this, then it's sort of like P1 and P2 are one object. So instead of talking about this object here, we're going to describe each of these objects here in terms of the instances that map to it. So for example, we could have an author who's called A1, A2, and that's since A1 and A2 are correspond to the names Joshua, Goodman, and Jay. Goodman? Yes. That would be sort of the description of that particular object. And of course, there's sort of an issue. This is all modulo some combinatronics, right? Because P1 and P2 could map to this one, or they could map to this one, or that one. So you'll have to adjust for that. All right. So one thing that's useful to note here is that each of these iotas corresponds to, well, once you've actually set this iota, you know what the structure of the base net is. Like, I guess that I didn't even talk about how the base net structure could be different, right? All right. Okay, so the thing to note is that for these different iotas have different numbers of objects in them, right? So since there are different numbers of objects, there will be the structure of the basenet, the number of nodes in the basenet and the way they're connected will be different. But once you know what they are, you know exactly what the structure is. And I mean, it was kind of, sorry.
Is it one-to-one mapping or many-to-one mapping?
Between what?
So given RPM, a fixed RPM,
Mm-hmm.
does it map uniquely to one single basenet in terms of dependency?
Well, like an original RPM does, right? Because like an original RPM has like this iota mapping like this. So each instance is exactly one object. But once we add this identity mapping to the whole to the world, I guess, and we have to start thinking about it. We can think about it. We can sort of think about the situation as if there were different basenet structures corresponding to different iotas. Does that make sense? Yeah.
So just to clarify, when you're talking about objects and the equivalent relationship, you're saying that the object is a particular structure of a basenet and different papers are instances of that particular structure, or I'm a little bit confused about what.
No, an object, let's see. Well, I was thinking about objects in sort of the logical sense, where you have like terms and this is all grounded in like first order logic, right? So you have terms, observations, like names for your observations, and then you have actual objects in the world. And we're referring to these objects using these clusters of these observations that we've seen. I mean, could you repeat the question? Like what?
Okay, so then, so how does what you're presenting there
Mm-hmm.
map onto the RPMs that you were showing before?
These ones? These ones?
Yeah.
These ones. Come back. These ones?
Yeah.
All right. So here, so here you have one of these things, right? One of these equivalence class sets. Well, identity mappings. And you will notice that each of these things, is like an instance of a class, of a paper class. So instead of each P being an instance of the paper class, it's each equivalence class that is now an instance of the paper class and has its attributes. So you see here, P1, P2 is the thing that has a title and an author. Is that making sense, or?
Go on.
Hmm?
I'm still a little bit confused, but please go on.
But could you say again what the first question you asked was?
I guess
Yeah.
I'm confused because I don't quite understand how the models that you're showing there correspond to, how you were getting to the one-to-many relation where you have all the objects and then you have all the instances in the paper.
Is it the combinatorial thing, like? So like, say there were you knew there were 4 objects in the world and 3 instances. Any of these instances could correspond to any of the objects, right? And you could write down, I think actually only 6 possible ways that they could combine into equivalence classes, right? Because these 2 could combine together, these 2 could combine together, these 2, 7. Each one could be 7? 5, sorry. Some number between 0 and 10. No, I don't know. Yeah. Sorry. You had a question?
I was just going to ask on the next slide how the bottom graph differs from having a single paper with a single author.
Well, you do have a single paper of a single author in this graph.
How is it different from the without the identity assumption? Without the uniqueness?
Well, no, it's basically the same. This is the graph that you get if you assume that there is a single paper author with a single paper of a single author. But there are 2 citations, so you could also have 2 papers with a single author, which is this example, Or you could have 2 papers with 2 authors. So each of these specific graphs could be like a graph corresponding to a specific RPM with a specific set of instances.
Okay.
It's just that
I didn't realize there were 2 citations.
Oh, so I guess it's kind of not very visible because they're both in green and they're on top of each other. There's a pale green citation and a dark green citation. No, anyway. Any questions more? No? All right. So before we had this set of random variables of these attributes x, right? What I'm calling them x because that's what you call random variables. All these things like, paper, that authors' names and authors' papers and things like that. And now we've added this additional thing, the identity mapping, to this set of random variables. So we need to define a distribution over both of them together. And I guess we could do it in a number of clever ways. But I'm going to just talk about just factorizing it like this. So first you decide on a distribution over your, sort of a priori, over your iotas. And then given your iota, you have a distribution over the other variables, right? And we already know what this is because these are, these graphs that we've already seen, right? They're basically what's defined over the PRM. So we just have to define a distribution over these. And this is a distribution that's, it's over how the different things cluster, how the different observations that we've made cluster, but it's made a priori. We don't know anything about how, about their attributes at that point, right? When we're looking at them without knowing their attributes yet. So basically, the only things we can think about here is how likely it is that things cluster sort of all together, and how, or maybe how many of objects there might be in the world, that sort of thing. So we've generally used just some kind of maybe exponential distribution over how many objects there are, and some combinatorics to account for the stuff that combinatorics. To account for the fact that the different clusterings could come about in many different ways. Okay. So in order to do inference properly in this setting, right, where we have both these things, we should really be summing over all these possible, since what we have to do inference with is these graphs, we should really be summing to do the full Bayesian thing over all the possible mappings. But this is just crazily intractable because iota can have a very big state space. So the idea is that we can either sample from it or search through the space of these iotas. I guess that's pretty obvious. But the thing is, you have to be somewhat clever about it. So the main thing we tried with the citation stuff was MCMC sampling. And I don't know if people here know MCMC. It's a sampling algorithm where you have a Markov chain over some state space. And you set up your transition probabilities so that as you're moving through this Markov chain, the fraction of time you spend in each of the states corresponds to the probability of that state. And one way to set that up is using this thing called Metropolis-Hastings algorithm, where if you're starting out at some state, you propose a new state, and then you using some kind of very clever proposal distribution which basically makes or breaks the whole chain. And then you accept it with this probability that's basically the ratio of these proposals and the ratio of the, well, pi is a MCMC notation, the probability of these two states. So basically you have to calculate the ratio of the probabilities of the two states. And this is kind of neat because if you're going to be proposing fairly small jumps in the state space, then these things will cancel. Large parts of them will cancel. So yes,
Sorry.
Yeah?
Can you go back one slide?
Yes.
When you say they can cancel, you mean you don't need to actually compute the pi's?
You don't actually need to compute the pi's because you're only interested in the ratio.
I see, but you do compute the ratio. You aren't saying that, you just assume the ratio is 1.
No, it will not be 1 because this would be like the probability of one state, and this would be the probability of another state.
Right.
Yeah. So, I mean, I think I have some examples, but I mean, if you just look at these things, right? If you were moving between these two, then, for example, like these parts are all the same, right? So you wouldn't have to think about them. If somebody had a hand up back in the back? No? Yes?
So with these different models, do they have different size state spaces? For different iotas,
Yes.
values of iotas, they have different state spaces?
Yes.
Then how can you use MCMC if you have changing state spaces?
It's still a well-defined probability distribution over all the possible state spaces. I mean,
Yeah, MCMC is typically, straightforward MCMC typically assumes that you have the same state space, and people use reversible jump Monte Carlo when you have different size state spaces, and you have to introduce a new term to deal with the dimension adjustment because the parameter space is different.
I know. I'm sorry. I thought this through a long time ago, and I know I thought this through. I can talk to you about it later when I remember. I'm sure it works, and it's in my thesis. I'm sure. Anyway, sorry. Yeah.
I did some stuff similar to that.
Oh yeah.
In this case, you can view it as a reversible jump if you want. It's
Mhm.
just that the x and the x prime are not living in the space of the same dimension. So really, you're dividing things that are not exactly in the same, in the same units. But it's okay because phi of x prime will be on the same unit of q of x prime, and then q of x will be on the same, live in the same space as pi of x, and they cancel properly. And so you can do this as a reversible jump if you want, but you don't have any extra funny terms at reversible jump. If you want to think of it that way, then it's one of the cases where reversible jump just has a little factor of 1.
I wanted to go back to your statement, talking about how easy it was to compute the ratio to pi's.
Mm-hmm.
To get the pi's, don't you have to do inference on each individual base net? No? Yes?
Well, not all of it. No. The pi is just the pi is just basically the joint, like
P of x comma iota, right?
P of x.
Comma iota.
Yes. Yes.
So don't you need, and then you had P of x given iota, don't you need to do?
This is basically P of x, and I guess here I'm thinking about x as x and iota.
Uh-huh.
Sorry. Yeah.
It's fine.
Yeah. So you'll be comparing to, well. So like you saw here, even when you have different iotas, right?
Uh-huh.
Parts of the network will be the same.
Right, but the probabilities of the random variables won't be, because they'll be the result. Should they be the result of belief propagation on each base net?
No. The pi's are just this.
So you don't need to do belief propagation to get that?
No.
Everything is instantiated.
Yeah, it's right. At every step of the
Got it.
you're in a specific state. Yes.
Got it. Where the random variables have instances. Got it.
Yes.
Okay.
Thank you. So that's actually one very nice thing about this situation. Yes. All right. So since each state is a fully specified assignment to everything, it's a fully specified iota, so we can just compare these network structures. And as I was showing earlier, and this, large parts of the state space will look the same. So here we're moving from the situation where you have one author and one paper to a situation where you have one author and two papers, and two authors and two papers. So these are the three possible network structures. Yes?
So you're doing an MCMC chain over the space of partitions, right?
Yes.
But once you pick a particular partition, how are you getting the rest of the structure? Do you fix it? What do you learn it?
Rest of the structure?
Yeah. So, I mean, there's variables that you're not partitioning over.
I mean, once you've chosen the particular partition, this is each of these is a full iota. It's like a full description of the partition. So you have a specific basenet defined. Once you've chosen the whole set of partitions. I mean, is that answer your question, or? And I mean, I guess there is a question that once you have these iota, how do you do inference? How do you do you just solve it exactly for this basenet, right? And actually, in the experiments we did, most of the time, well, these things were still very high, very intractable, because when you have many different papers and many different citations, you have many different things with lots of parents, and I mean, they're like fully connected as parents and children, right? So we also did. So this was Metropolis Hastings. We also did Gibbs on the specific values of the different other variables. So here you have like MCMC over the different structures, and here you have MCMC over the different possible values that the different variables could take. So it was sort of like a two-layered MCMC. But actually we found that, why did I press that? Actually, we found that, when you have a lot of data, it sort of stops being Bayesian. I mean, doing the full Bayesian thing stops making sense, because there is one thing that usually that really dominates, especially since we were clustering together all the, like since we were treating all the iotas that were sort of just combinatorially different from each other together. So, so in a sense, I think near the end, I sort of figured out that the MCMC was basically doing sort of simulated annealing type stuff. I mean, except without time. It was basically just seeking out the best thing. It was just doing search. Anyway, the basic idea of this was, I mean, I guess it's a pretty obvious idea, really, is that although relational probabilistic models in themselves have very large, are very complicated with lots of connectivity, and then you add this identity uncertainty thing, and you add even more complexity. If you're making just these small steps, a lot of stuff cancels. So you only have to do very simple calculations. And so we did experiments on this. And this is the model we used. It's a lot like the one that I showed, except we had we were thinking about actual authors and sort of the authors. Since we had a many-to-one relationship between authors and citations, we took the author out of the citation and gave it its own class. And then you would get basenets sort of like this, where all these different things were affecting what the text of the citation would actually be. And at the time when we ran the experiments, they compared very well to what the best thing at the time was, which was phrase matching. And also one benefit of this, of the actually doing the full Bayesian MCMC thing, is that while this was only solving do these two things co-refer, you can basically answer. You could ask the MCMC any sort. Well, you could ask that algorithm to answer any sort of other question, like how many authors are there? Well, you could ask it how many authors are there, a posteriori in the domain, or like how many different authors publish things with face. I guess I should say more about this. These are 4 different data sets that we extracted from. That actually were extracted by this, I think, by the CiteSeer people from a large corpus of citations. They were the citations with these words, these specific words in the title. And they were like, each of them was like a large number, like maybe like 700 or something like that, citations corresponding to which was a lot at the time, corresponding to like half as many papers, with some papers having 20 citations and many of them having just 1, right? So anyway, so those were the results.
How long did the MCMC take? A few years, which
ages. No.
Ages for how long? Did
No. It took like I don't know, like a couple of hours to run or something. I mean, of course, you don't really we don't really know when it's finished running, right? So we had I was running like several different chains and then comparing their variances to the like variance of all of them and stuff to decide when to stop.
How big of the focus? How much data points do you have? How many citations?
So each of these was like 700 or something citations. And there was some other interesting stuff going on here. I mean, we were basically parsing the citation text because it's not really that, the citations come in all kinds of different formats, really. So this is not an easy problem. And now I think Andrew McCallum has much better results for this, and he's got like an actual proper parser doing this instead of a random heuristic one that we hacked up.
Did the results of your models feed back into how you parse the citation? I mean, I know I've parsed citations before, and like sometimes if you know someone's name from somewhere else, that'll help you decide who the authors are.
Well, that should sort of come in here come into this model by itself, right?
So you reparse you.
Well, no, there's several possible parsers. So actually what we did is we wrote like a hacked up parser and took like n best possible parsers, and then we would move over these parsers, treating them as if they were a random variable.
So Andrew McCallum uses a conditional random.
Yes, his stuff is newer, and
This is a very different thing. This is generative model, the one you're talking about.
Yes, and I will be talking about conditional random fields in a moment.
So you think the difference is due to the different style of the model rather than.
Yes, but it's a good idea to use a model that works better.
So you talked about how you did inference in this model. Did you learn the probability?
We learned we learned the parameters here, except for how to do the parsing, which we hacked up. And it was, it was basically like a stochastic EM where we used MCMC to fill in the unobserved things, and then we learned the parameters that way.
So you trained, like on the next slide, you have 4 sets. Did you like train on 3 and test on the 4th?
I think on each set we had like 5-fold cross-validation or something. Yeah, I think. Look it up. I should have looked these things up, shouldn't I? Huh. Anyway, yeah. So so to get back to the rest of the talk, and also to the point that somebody just brought up, so I'm going to be talking about different style of model now, undirected. And one problem with this sort of directed model is that while it's we all know generative models, they're sort of intuitive. If you know exactly how these things are generated, you can write down you have a pretty good idea of the structure. You can write down the model structure. It's neat. But there's lots of there can be lots of dependencies between different things that you need to capture, and you also need to write down priors. And I'm not actually sure. So in order to write down a prior for iota, the iota prior, we had to have a distribution over the number of authors and the number of papers. And what on earth does that mean anyway? I mean, we ended up having them pretty flat. All right. So.
Let me just interrupt for 1 second.
Oh, sure.
So I don't know how much of your talk is left. I know.
Not that much.
Okay. Good. I'll shut up.
But this is
take
the.
your time. The audience has been asking lots of questions, so if you had a lot less, I would ask the audience to shut up. But it sounds like everything's going great.
No, it's fine. Yeah.
Okay.
I mean, I have like 15 minutes
You have
left.
actually more. No, take your time.
Yeah.
Take your time.
All right. So I'm sure everybody here knows as well undirected graphical models. And there's probably bugs on the slide. Well, anyway, so now instead of writing the joint as a product of these conditional distributions, we're going to have a product of potentials. Did I ever write down the product? Yeah, here. Yes, product. Again, we have a graph. Each node is a probabilistic variable, and the edges sort of form cliques, and then we define potentials over these cliques. So each clique in the graph has a potential function, which is a log linear combination of features of that clique and weights, I guess is one way of writing these things down. And one thing about these things is that they can be used discriminatively. So we don't actually have to write out the prior of the prior of the hidden things. We can just only do the inference. I mean, we can have this distribution be a distribution of the hidden given the observed. So we're only sorry. So the distribution is only over the hidden things, and we're using features over both the hidden and the observed things, which I guess I should have put on the slide. All right. So this is so now this is the new problem that we're going to be dealing with. So we have this data that the robot gathered by walking around this building, and it's represented in terms of a Voronoi graph, which is like a graph that picks like sort of divides up the space. So it's every point. How does it go? Every point. So every point in the space belongs to like the closest point to it, but that's not really relevant anyway. Okay, so anyway, we have this graph over the space, and the graph has little nodes of observations on it, and each observation is just a range scan of the surrounding area. So and for each little node, we're going to try to figure out what type of location this is. Oh, thank you so much. Excuse me for a second. Yes. So this is going to be like this is obviously an undirected. It's like it's a conditional Markov field, and there are two kinds of clicks here. We have these clicks over the observations and the place type associated with the observation. So that's basically like features like what features do we use? I don't know, like the sort of the features of the general shape that the thing found. Like, can you fit a line to it, and then does it have a low variance? Does it seem like a sort of curvy sort of space? How large is it? Stuff like that. And then you have these cliques over adjacent, the hidden type nodes, right? Which tell you constraints like, is a door likely to be a hallway or something like that? So so for this example, each location can be a room, a corridor, a door, or a junction. So these are different colors representing them. So then when you have a little fragment of the graph like that, you can assign values in different ways. For example, this sort of makes sense. It's like two corridors that meet at a junction. Here you have a room with a door going out of it. This is, it makes sense, right? This is like a little piece cut out. And here you have a complete mess that doesn't make any sense. It's a door in the middle and stuff. And I guess the problem with this is, even though it works quite well on a sort of local scale, you also want to be able to make. You might also want to make sort of more global. So sort of think about more global information. Think about these actual places themselves that you're creating together, that you're creating by putting these things together, and think about their properties and see if you can use that to improve the local classification, right? So for example, corridors are not just things that tend to have small sort of longish tube chunks next to each other. They are not just things that tend to be sort of tube-like and next to other things that are corridors. Corridors tend to be actually very long and tube-like altogether, and sometimes they take sudden turns. Or rooms actually might also have these, if like there's a lectern or something in a room, that bit behind it might look actually a lot like a corridor, right? But then if you put it all together, you realize that that's actually just part of the shape of the room. And it doesn't really make sense to have like a little corridor in the middle of a room. So we're going to try to add this higher level information to these things. So, okay, so this is like a segment like we've been looking at so far, right? It's got these different type nodes for the specific locations from 1 to n. I'm just, without loss of generality, restricting myself to a straight line. And then you've got all the observations at those specific nodes. And since we're now not actually defining a prior, because we're not in like a generative world, we can't actually do that nice trick where we sort of took the iota out and defined it by itself, and then defined different types of networks depending on the iota. The identity uncertainty part is going to be part of this graph. It's going to be sort of implicit in it. So what we're going to do is we're going to add higher level nodes where, so this x1 represents the type of place that x1 is, and xi through j represents the type of place that you have between I and j. And it could be a specific place if they all match, or it could be a conflict if they don't match. So actually, people have been using this sort of technique to reason about whether things are the same. So like Andrew McCallum's stuff on citations, he doesn't have this nice corridor structure, so he thinks about all the possible ways that citations could co-refer, and he creates these sort of indicator nodes for them. But that's just true-false, and we're not doing true-false. We're doing false, and then if it's true, if it's true, we're actually reasoning about the possible values of the attributes of that object. So we're not just thinking about object existence, but also about object properties. So anyways, okay, so there are two different types of cliques now. There's each of these places, a place being a bunch of sort of consecutive nodes in a sense, and the observations that correspond to that place, because we're going to be extracting features from them. And then there's also deterministic connections between places and sort of lower in the hierarchy places, because we're going to be building up a whole hierarchy like this, where so we can ask a question about any possible piece of this line. So every piece of this line exists, somewhere in this little triangular graph. And if you think about it, like at the bottom level we have n things, then we have n minus 1 things, then we have at the top we have just one thing from 1 to n. There's like half n squared nodes here, right? So it's actually not that bad because we have a straight line. I mean, if we were considering all possible things clustering together, like with citations, it would be exponential. But it's still a fairly large, highly connected network. But does it make sense to people what's happening in this network? Yes. So now we can. Okay. So for example, here is how we're going to do assignments on this network. This is the node that represents everything from here to here, right? Oh, that's actually wrong, isn't it? That shouldn't be. This is yellow, by the way, and this would be green, because this node actually represents everything here. Like this whole pyramid. And the yellow nodes are conflicts. So we're actually using yellow to represent both, like these two things are different, and this thing is just a subset of a larger place. And the reason we're doing that is because we want to sort of use a similar sort of algorithm, which is moving over the state space of these things, making small jumps without calculating too many things. And if we represent it this way, we can, this is wrong. Sorry, this should be down here.
Sorry, I'm not sure what the colors are supposed to represent.
The colors represent, like before, like when I listed them here, the different types of places. I'm sorry,
Yellow?
And yellow is a conflict. So here, this should be yellow, say. Well, actually, let's say this is green. Let's say this is red, and this is yellow. So that would mean that all of these things are green, because this node kind of corresponds to all of this, right? And this should be wrong, and this thing is red. So that would mean that this is all a room with a door, right?
So are the nodes below, say, the green, all the yellow nodes below the green?
Mm-hmm.
Should we think of them as green
We could, but that would not be, that would mean that we have to do a lot more complicated calculations in our. So actually, this is kind of well, basically these the idea is that these yellow nodes don't actually learn anything all that useful, because it's really hard to learn just a little log linear classifier over all the things that are not any kind of place, right? Because there could be really tiny things, or they could be everything in the whole world. Neither of these is a good description of a place. So I think they're just sort of more like balancing out to making sure the dimensions of the different things we compare are the same. Again, this should be down here. So if we let all these things be yellow, then when we propose steps in this state space, again, we don't have to change that much stuff, because most things stay yellow. So if we're changing from this thing, which should not be here, to this thing, all we would have to change is the nodes that. Basically, all we need to think about is the nodes that changed from this state to this state, and ignore everything else, so we can make really quick steps. So it's basically the same idea. And I had a slide of results, but it seems to have disappeared when I put it on my laptop. I'm very sorry. But anyway.
Say anything about the results?
Well, basically, we just, like the idea, if I go to the beginning, basically, they just give us slightly better assignment of places. So if I don't know, I should just go back to the beginning and show you that slide where you sort of chop up the state space into different things. What we do is we start out before we were just taking the best single assignment on the lowest level, right? So we start out either at a search, like either a greedy or a stochastic search from that, or I guess we can do MCMC too. We just don't find it that useful. And try to see if we can improve on that using this knowledge. So for example, if it's found some kind of tiny thing like this, like a tiny little corridor inside a room, it looks at all the possible places it sees. It sees that corridor seems to have a very, very low, seems to be contributing very, very little to the likelihood, and it thinks, well, maybe I should do something to that corridor. It's very humanizing way of thinking about it. And then it will switch that corridor to a room. So it will discover that it's a whole room with just a little piece of thing hiding behind some furniture. So that's the sort of stuff it finds. So it improves the situation slightly. And it will improve it much more when I get through with it.
One more question.
Yes.
So I don't understand the graph structure. So
yes.
Like there's the red node.
Which is wrong.
The two yellow nodes directly below it.
Yeah.
Why is it connected to those? Instead of just, is it connected to all of the lowest level nodes and the ones directly below it, or?
It's everything is connected to just 4 things. So so I can So if you are I through J, you'll be connected to I, and you'll be connected. Is that right? Why did I put so many things in here? No, that's wrong again. Okay, so you should be connected to I, and you should be connected to J, and then you should be connected to I plus 1 through J, and to I to J minus 1. So like you combine I to J minus 1 with J, and you combine I with I plus 1 and J.
Okay.
So that's all you need to do to put in all the constraints. So it's actually not that bad. Yeah. So the general conclusion is that this is a sort of general framework for handling this sort of problem, and it can be used with different types of graphical models, and certainly different relational extensions to them. And it's certainly useful in many different applications. I here showed just one that's text and one that's robotics. We also used it for a tracking application. And the general idea, behind the algorithm is you just take these, figure out a way of taking just very small steps, I guess iota space, in the in this space, and then a lot of stuff cancels. I mean, it's not a very crazy idea, but it's the way everybody's doing it. Anyway, any questions? And I guess the main contributions of this talk were that the identity uncertainty was kind of my thesis stuff. And now I'm coming back to that stuff, and I am actually using, I'm not just reasoning about which things co-refer, but also about their attributes, which people aren't doing. Let's start on the left here.
You mentioned at the beginning that since you could use this in different applications, that you could take some of that knowledge from one application area to another. How does that work?
What knowledge?
That I guess the rules or the.
I don't remember what I said like that, but that you could take well. I mean.
So these are all completely separate.
I mean, the general idea is the same, and you could certainly, you could certainly imagine writing some kind of general framework where you'd have a language for feeding these things in, and you would have to give it some kind of guidance as to what kind of steps to make in the search space, because that's the hardest part. I mean, that's pretty application specific, right? I don't know. Did you have a question? Yeah.
So citation analysis, what's your prior over?
In citation analysis was the prior of IOTA. It was basically just like exponential decay, I think, cut off at a certain point for over some large number, over the number of authors and number of papers in the world. And it was adjusted because IOTA is each IOTA represents many different ways that things can match up. It was adjusted, with I've forgotten whether it's combinatorics or combinatronics because I'm a foreigner. But is that the answer?
So the notations are relatively, the size of each set of notations is relatively small.
Well, we used very flat. We ended up with a very sort of flat prior that didn't really, that basically assumed that the different partitions the different assignments were uniform almost, with some preference for smaller numbers.
The citation matching, was the ground truth human ground truth, or was it the scientific Perl?
It
was human ground truth.
You have to know how well on that same data. They don't just do phrase matching. They Lawrence and his giant Perl blob that sort of did it. You have to know how well your system did versus his giant Perl blob.
On that particular data, at that time we did better.
Okay.
But I think now they're doing better.
That was 4 years ago, right?
Yes, true. Yeah, and and also actually, it was hand labeled by somebody at Sightseer, and I think that there were a couple of mistakes in the labeling, which I guess mix up everybody's algorithm equally, so it all works out in the end.
For the citations, in the labeled data, was everything labeled, or only, for example, identity, or?
Only, the only thing that was labeled was whether things co-refer. So every citation was given like a unique identifier, so you could figure out which ones actually co-referred.
Thank you very much.